Welcome to the presentation of 33rd Street Outfall project. Hi, my name is Steve Choi. I'm project manager with the City County Denver. Jeff Holste is the project manager with the Wilson and Company. Jeff and I have worked on this project past 5 years. I'd like to go over briefly the presentation overview, which has basically 4 parts: project stakeholders and background for the project and city's drainage goals, and walk through the segments, each segment that has 4 segments, and lastly, key construction elements of each phase. There are numerous stakeholders for this project, and also a large number of project team members who made this project success and possible. Drainage deficiencies were identified in 2009 Denver Storm Drainage Master Plan. As you see on this drainage map, the total drainage basin is about 4.5 acres. This map has basically 2 main basins. One is Lower Platte Valley, lower half, and the other one, 36 and Downing Basin, it's on the upper half. The basin is basically fully built out with the older residential neighborhoods in the upper basin and the commercial in the lower basins. And the basins include Union Station, Coors Field, Ware Yards, and Rhino Art District, along with the several residential neighborhoods, including Five Points, Cold, Whittier, and the City Park West. The basin lacks outfall, and the existing system is very old and has a less than 1 year capacity. As you see on this slide, some of the existing outfall are 100-year-old existing brick systems, which are relatively deep, and the detailed brickwork is quite impressive, and they're in very good condition, but they are majorly undersized for today's flow requirements. Every project has a goal. This project is no exception, and the goal for this project was to adequately address the areas where significant flooding occurred, and the upgrade level of drainage system service to a 5-year capacity. The challenge was how to determine the overall most feasible outfall alignment navigating through the heavily urbanized streets. The drainage capital improvements were proposed again in the same Denver drainage map. And the several major outfall interceptors were primarily recommended because the existing lateral network was already established. As a result, 33rd Street outfall was selected as one of the major outfalls. In next slide, Jeff will talk about some of the components and the challenges for each phase of the project. Jeff?
Thank you, Steve. Yes, as Steve mentioned, the 33rd Street outfall ended up being kind of the optimal corridor for improvement of the drainage configuration for the basins north of downtown. That included an extension of the alignment from the South Platte River to Marion Street, and that was about 4,400 feet of corridor. This alignment allows us to connect into 3 different existing storm sewer systems along Walnut, Champa, and Downing. And these are all existing brick systems that we were able to intercept flow prior to any of that flow reaching the existing outfall location. We also had a lateral along Blake Street and Martin Luther King Jr. Boulevard. These laterals were critical to provide some relief for some sump areas. And ultimately, the 33rd Street outfall connects up to an existing 84-inch storm sewer with the use of the Marion Street system, which is currently in construction. The overall project corridor includes a wide variety of conduit sizes, and the primary conduit for the outfall was a 10 by 8 or 11 by 8 box culvert. We also had some combinations of other sizes to allow us to widen and have a shorter structure where cover issues became a concern. We also had a 10-foot diameter Holste pipe, which is a unique pipe in itself, with centrifugally cast fiberglass mortar pipe. And so that was used for this project on some locations where we had both open cut, but primarily on the tunneled sections. So phase 1 of the outfall starts at the river and extends upstream to the Union Pacific Railroad. This area crossed several private parcels, a lot of commercial type developments, and large residential apartment complex type developments. And this area was certainly an obstacle in terms of timing and potential conflicts with existing development that was ongoing through the area. Added to challenges for construction and changes throughout the corridor almost on a daily basis. As we started at the outlet of the conduit to the river, it was a great partnering opportunity for the city to partner with Mahi Flood District. And the district really took on management and funding of an outfall structure. And they worked with some of their key partners, Mueller Engineering and Stream Design and Pinion Environmental, to facilitate construction and design and construction of that outfall. As we worked upstream, one of the main construction constraints we had, which resulted in a large vertical difference between the outfall elevation and the river, were 2 sanitary interceptor sewers. And these sewers vertically were just not able to be crossed under. And so we looked at an alternative to raise Arkin's Court in this location and actually cross above these sewers after they had been protected. To cross over the sewers at this location, the outfall conduit actually transitioned to a dual 18 by 3 box culvert structure. And this allowed for a wider and shorter structure to then discharge to the river, and also allowed flow to dissipate and spread for easier energy dissipation at the outlet structure. As we worked upstream from that transition, the Arkin's transition structure was a combination of transition from dual 18 by 3 boxes into a 20 by 4 box culvert. So this was one of our first transition structures along the corridor. Very large footprint to provide that smooth transition and very shallow cover condition. As we worked further upstream at Brighton Boulevard, we began the first one of our first open cut and tunneling segments. This tunneling segment had a 10-foot diameter Holste pipe that was jacked from the Brighton jacking pit to the east, and this was constructed along a very narrow private development corridor. The impacts of working through this type of a corridor, we really, the contractor was very tight on space. We had a 30-foot easement in place due to limitations on existing structures, and also the planned construction of a hotel. And so we had a tight corridor as well as a very narrow window of opportunity to get this alignment constructed. The contractor did a great job working with the city to make sure that this was accomplished. As we worked through this corridor, the contractor really was able to utilize the slide rail system as a big benefit for construction of this large conduit at depths of 18 to 25 feet through the majority of the outfall. The slide rail system is an active shoring system that has rails driven in, and then slides that are placed between the rails as excavation occurs. And then these slides are advanced down as materials removed from the trench. This is a view of our storm sewer corridor after construction. The photo on the right, you can see the overhang and the tall hotel that I mentioned. That corridor is the home now to that storm sewer system as well. So very, very tight situation. It would not have been very feasible to construct after all these buildings were in place. As we moved east then, phase 2 of the project included extension from the Union Pacific Railroad to Blake Street, and this included crossing under the railroad. This segment has 4 individual tunnels and really was unique in terms of working in the Coors Field, north entrance of the Coors Field parking lot. And it also was an area where public involvement and outreach really became evident as a critical feature as we worked around apartment complexes and smaller individual businesses. These challenges through this corridor included delays in just getting permits in place from both the rail and other entities throughout the area. As we worked on crossing the railroad, the first component was for the contractor to construct a jacking pit for the tunneling operation. This was a large structure that allowed for placement of rails and jacking equipment to extend the 250-foot tunnel underneath the railroad. First step in that tunnel system was to provide a grid of horizontal bores. 9 horizontal bores were extended out along the tunnel alignment, and these primarily were focused on identifying any potential obstacles or material that could cause a delay to the tunnel or potentially a tunnel failure. Ultimately, 2 12-inch steel pipes were also inserted along the bottom portion of the pipe as guides, and that 10-foot diameter tunnel was advanced using those rails as guides for steering. The tunnel ultimately, as I mentioned, is 250 feet extending out across the railroad. The tunneling head was a individual, 2 individual pieces that were formed together in the tunneling trench. And so as they were advanced, there were sand shelves provided on the tunneling head, and hand excavation was utilized to remove material and place it on a conveyor system that was located within the tunneling heads themselves. These photos are a view of what that looked like with the sand shelves in place, and as I mentioned, the hand excavation and removal of material. To advance this tunnel, the contractor actually worked for 50 days continuously with this tunneling operation to complete the tunnel. These are a couple more photos of the 10-foot diameter set and 10-foot long sections of the Holste pipe being lowered into place, and then the large jacking system and hydraulic cylinders for advancement of the tunneling system. As we extend the outfall further east, we cross Blake Street. Blake Street's a major corridor, especially for communication in and out of downtown Denver. And with this corridor were a lot of conflicts with utilities. And so construction of an open cut across Blake Street was not a feasible approach. And as we worked through design, we had indicated this was going to need to be a tunneled section. The contractor was able to jack in place 2 8-foot diameter tunnels, steel cased tunnels under Blake Street. And in this situation, the tunnels were epoxy lined, and the railroad tunnel, it actually should mention that the Holste pipe acted as a carrier and a casing pipe. And so we had a single pipe installation for that tunneled operation. On the east side of Blake Street, we had a junction to transition from a 10x8 box culvert to the dual 8-foot diameter tunneled pipes. And we also had the connection of a 54-inch lateral system for the Blake Street lateral. So the receiving pit for this jacking operation was then able to be utilized as shoring for a cast in place transition structure. Along Blake Street, we also had a segment of 53-inch Holste pipe that was micro-tunneled. This is the configuration of a micro-tunnel head, and then also the head that's being advanced on the right photo. Micro-tunneling is a closed-faced system, and so the slurry of material is removed from the operation and ran through a processing plant. The tunneling head on the left is being removed from the end of the microtunnel by the excavator at this point. We were able to advance the microtunnel along the corridor because the adjacent buildings had been installed basically and constructed after the project was already out to bid. So that very tight setback was a limitation for the project, and the contractor was able to make that adjustment and utilize the microtunnel to keep the project moving. As I mentioned, communication for the project was very critical. We had a public relations consultant that was on our team and worked to update the community, provided feedback at meetings, and then also updated and communicated with the city for updates to the city website. As we extend further up the corridor, Blake Street to Curtis Street was the phase 3 segment. This was the longest individual segment of the project, and this was primarily a straight box culvert installation portion of the project. The main variation here was that this corridor was extended up to 30 feet deep, and so this was the deepest segment of excavation that we encountered, and certainly a challenge for the project. As we worked along the corridor, then the contractor was able to advance the slide rail system and work with a series of components to utilize 2 excavators and ultimately a crane to lower the box culverts in place. You can see the large box culverts in the right side of this photo. This operation was really made most efficient with the use of a crane to be able to lift components into place and move materials around. This large crane was a huge benefit for completion of the slide rail system. Progressing the slide rail requires a long reach, and the excavators just don't have enough reach to be able to have the entire system work together. That includes both box placement and the slide rail advancing. So you can see here the crane can move material at a further distance and place those boxes, and then excavators were able to pick up where that crane left off and finalize those into ultimately the final configuration. As we worked along this corridor, that 30-foot deep connection was a major challenge, and as the contractor removed the upper 3 to 4 feet of the roadway and subgrade, then they were able to install the slide rail system, work around utilities, and then progress that slide rail system up the entire corridor. Really, once they got in a rhythm, they were able to make great progress and move through this corridor very efficiently. As you can see, a lot of material was removed and cycled through for this trenching operation. As utilities are encountered, there are some configurations on the slide rail where gaps are able to be left in that slide rail, and then additional rails installed. Where those gaps for utilities are installed, sheet piling or H piling was also utilized for that shoring to make sure that those utilities were protected, and also for support of those utilities. And as I mentioned, as we work through this corridor, it's a full reconstruction. So we had an entire roadway section reconstructed, curb and gutter, driveways, sidewalk, ADA ramps along this entire stretch of 33rd Street. Finally, as we work up to corridor, phase 4 was the final phase of the project, and this included a segment from Curtis to Lafayette Street. This included a lateral along Martin Luther King Jr. Boulevard, and then major storm junction structures at Champa and Downing Street. And the main structure is the Downing Street structure, and this includes crossing of a 33-inch sanitary sewer. Crossing at this location is critical because the sewer had to be suspended to bridge across the excavation during the entire time that they were working on that excavation. The total construction in the Downing intersection included a 10-month window. And this included closures, working with businesses and schools in the area for timing, and also included new traffic signals at the intersection. We also included trash vaults along Downing, or down Martin Luther King Jr. Boulevard. And these trash vaults were really removal of floatables. And so they were offline structures that were configured to remove floatables from the storm sewer. These photos are some excavation of the actual system in the Downing intersection and the actual structure. It's a massive excavation of sheet pile and I-beam supports spread across that entire excavation. And then, as you can see in the right photo, suspension of that 33-inch sanitary sewer. These photos are a kind of a transition through the structure. The photo on the left is a curved transition The structure actually works to transition flow 90 degrees as well along the alignment. And in the photo on the right, you can see the vertical at the top of this ramp is a 63-inch storm sewer that had to be transitioned down to intercept the invert of the 33rd Street outfall. At this location, the outfall transitioned down to a 20-by-4 box culvert underneath the sanitary. And so there was a lot of forming and an extensive amount of concrete work through this structure to be able to accommodate this and accomplish this configuration. Really a massive feat, and we'll show you a video later that really takes you through the entire structure construction. This was a big accomplishment by the contractor, and certainly had its own risks as well. And so the contractor did a great job being able to accommodate that. And as we kind of move through that, then I want to toss it back to Steve to just wrap up a few highlights from the city's perspective for the project and close us out.
Thanks, Jeff. Well, the last phase of this project was completed in December 2019. Constructing the entire project in 4 phases over 5 years cost Denver over $40 million. That's a lot of money we talk about here. The drainage service, the level of drainage service was brought up to the 5-year capacity. And that was one of the project goals that I mentioned earlier. And we ran a flow TD analysis, and that the flow TD analysis indicated that for the most part, the inundation flow depth is 12 inches or less at the flow lines on the streets, meeting the Denver storm drainage criteria for a 100-year storm event. And this project was crucial to make sure that city and engineer and contractor was on the same page, and collaboration, huge amount of collaboration has taken place. As Jeff has addressed in earlier slides, each phase had new challenges. Now, this project laid the groundwork for 27th Street Outfall and Marion Street system, 2 of which are major outfall interceptors, and both projects are under construction. Now, the next slide, it's a time-lapse video of the Downing intersection improvements, including downing a massive junction structure, condensing 10 months of construction into 2 minutes. Thanks for watching.
Thank you for attending our presentation, and we look forward to questions.
Thank you.